Hello everyone to the second video lecture. I'm going to start today by teaching us a little thing on Excel. So here, let me share my screen here. I believe you can see me. So I need to do a bit of a warning. Unfortunately, because I'm using a Mac, this is really only going to be directly applicable to those who are also using a Mac. I believe the Windows version is very similar, but if there are any discrepancies between what I'm teaching now and your computer, I would encourage you to look at online manual pages for this. There are a lot of really good resources, and if not, just come to office hours and I'm sure we can work it out together. So what we're going to learn today is how to make a scatter plot in Excel. So what I have on the left here is my data, and I've actually already made one here, but I am going to delete it so that I can show you how to make it. What you want to do is I hold Command so that I can select two columns. I'm going to make a scatter plot, poverty versus income. Then go to Insert, and I have this little scatter plot looking icon. I'm going to select a scatter plot. Oh dear. Oh, I think it's because I had something right here. Let's try that again. There it is. So, and Excel, just as easy as that, will go ahead and make your scatter plot for you. So the x-axis here is x-axis here, which I can actually edit this way, is poverty. And the y-axis, which again, using this little tool in the chart design tab, is, what did I say was income? Nice. Maybe I will say, give it an informative title, which is a good habit to get into. So scatter plots are a very good way to visualize two variables of data. So every single row here, for every single row, we have a poverty value and an income value. So for a single row, that corresponds to a single point in our scatter plot, which I think we talked maybe a little bit about in our last lecture. One other thing I want to show us before we move on is if you select this Select Data tab, you can actually, so I have poverty on the x-axis and income on the y-axis. If I wanted to perhaps switch those, I can do so down here. Some people you can press the switch row and column, but it never seems to work for me. So what I do instead is, so the x values refers to column F, where poverty is, and the y value, which refers to column I, where income is. I just go ahead and switch those two letters. So now x values are going to be referring to column I, and y values are going to be referring to column F. And when you do that, it'll flip them for you. I believe you'll have to manually change your axis labels though. So this is a great way to visualize your data. And I believe on your homework, you're going to have to do something along these lines. So now that we have covered that, I'm going to go ahead and take us through a number of definitions that we need to kind of be able to understand and use because they're very quickly going to join the vernacular when we're talking about data in this class. I wrote out a bunch of them already because I did this entire lecture once already and made a terrible mistake and threw the whole thing out. So here we are again, and it looks like we're going to be able to save time since I've already written up most of it. We're just going to talk about it and try to think about all of these definitions as much as you can. And I mean, maybe don't go as far. Actually, yeah, maybe commit them to memory. A lot of them are pretty intuitive, so I hope you remember them. So recall our statistical process. Our second step was to collect relevant data on the topic, and all of these definitions are going to have some things to do with that step of our statistical process. The first thing we want to talk about is population, which, as I have it defined, is the group of subjects to which our research question relates. It is often too expensive to collect data for every single case in a population. So say we wanted to know the average length of dog tails in the United States. It wouldn't really be feasible for us to find every single dog in the United States and measure their tail. Um, Usually we say it's far too expensive, but in this case, I'm not sure even if you wanted to, you could really do that. I don't know, more power to you, give it a shot. um, and because it's so expensive, if we want to say something about that population, we instead must take a sample, which is our second definition. A sample is a subset of the cases that is often a small fraction of the population. So rather than try to measure every single dog in the population, we take a sample of dogs and we use the information that we see in the sample to try to infer or make a best guess at qualities of the whole population. So these are our two big deals. I'm now going to start talking about things we want to avoid in this process. And the first one, which has a special, I have a special dislike of it. I hate it because I have an uncle who loves anecdotal evidence, which is data collected in a haphazard way that may not represent the population. And I have a funny little example here. A man on the news got mercury poisoning from eating swordfish. So the mercury concentration in swordfish must be dangerously high. I would hope all of you would see some of the issue here. Just because there is a single man who once got mercury poisoning and also ate swordfish does not mean that everyone who eats swordfish is going to get mercury poisoning, nor does it mean that swordfish themselves have an unusually high content of mercury. This is a particularly out of the ordinary case. That's probably why it was on the news in the first place. And we can't really use it to extrapolate and to infer the qualities of the population of swordfish. So be very careful with anecdotal evidence, and I hope if you get something out of this class, you should have a cynicism towards people who like to use it, because I think it's ubiquitous. People really like anecdotal evidence. They use it in ways that they really shouldn't. So the next thing we want to talk about is sampling bias. So this is when the method used to select a sample is skewed to favor a subgroup of the population. And I have a little picture as an example here. What we really want whenever we take a sample is if I wanted to say something about the population of all graduates, so every single person who has graduated college, or maybe graduate student, let's say all graduate students. So me, haha, I'm a graduate student. If we wanted to say something about the entire population of graduate students, we would want to take a sample that represented that entire population. In this example, though, they gave the person who wanted to sample was a nutrition major, and I think they say she. Actually, no, they don't. I just inferred she on this graduate major. Let's say she, but I don't know. I wonder if there was like a subliminal reason I did that. Oh, probably because the only nutrition major I know is female. Anyway, so she might take a subsample because she is in the medical sciences, maybe takes a sample of a bunch of other med students. And this would be very bad because our sample would then only represent the population of medical students, maybe perhaps on UNC's campus, which is not at all the population of all graduate students that we wanted to make inference on. So whenever you have sampling bias, this could be a very terrible thing because it may result in you making inferences and making statements about a population that you aren't actually representing at all in your sample. Another type of sampling, I guess a little bit like sampling bias, is convenience sampling. This is specifically when individuals are more accessible are included in a sample. And I must say this is very common on college campuses because often you want to do these studies on a college campus and you say, hey, all these students are here, let's give them extra credit or like free food to get them all to join the sample. But when you do that, you're not really catching the population of people who aren't as convenient, people who aren't on campus, people who maybe aren't as enticed by food as college students seem to be. So these are all examples of things you don't want to happen whenever you are creating a sample. what we want to happen, and in fact, what we will try to do in this class is a simple random sample, which is basically if you performed a raffle on the entire population, every single subject in the population has an equal chance of being picked, and you choose a subset that way. This corrects for sampling bias, it corrects for convenient sampling, and it corrects for this last little detrimental thing, which is voluntary response, which is probably one of the worst things you can do when it comes to picking a sample. It's when you ask for people to just send in their answers to the sample by their own, using their own time, completely voluntary. And this can be really bad because usually the people who take the time to answer a survey like that are the people who have very, very strong opinions on something and are usually at the fringes of what the average thinks in a population. So there was a poll by Ann Landers I've written there where she asked parents, if you could choose to have kids again, if you could go back to when you decided to have kids, would you still have kids? And I will just leave you all to look that up. It is very interesting. It is a great example of what you shouldn't be doing in a sample. So those are our definitions that I wanted to talk about today. I'm going to finish up this lecture with a brief talk about categorical data, which we've touched upon in a bit. Nope. Oh dear. We've touched upon a bit when we were talking about the stents data. And what I have right here is my little example of categorical data. I'm going to put a ... here because we're going to assume that this is just the very top of a data set, right? I'm just showing you the first 5 observations, but there are more. Every single row here is a single individual, let's say maybe graduate students again, and what we know about them is their name. We know their writing level, which is in a few different categories, categorical data, of course. They either have no writing level whatsoever, they're a beginner, intermediate, or expert. And we also know their major. And I believe this is also just limited to the categories listed here, so social science, STEM, humanities, and interdisciplinary. And whenever you get a data set that looks like this, you can draw something called a contingency table, which is this thing right here. And what you do is you write the different possibilities for the category on the margins. So here we have all the different possibilities for level of technical writing experience and all the different possibilities for major. And the elements of this table represent how many people fall into the intersection of the two groups. So what do I mean by that? I mean, there are 41 people who are in the social sciences and have a beginner writing level. In contrast, there are 13 people in the social sciences who have an intermediate writing level, right? That is how you read this table. You say, this is the number of people who fall into each of the two groups where the row and the column intersects. So whenever you are given a contingency table, one of the first things you should do is calculate the row and the column sums. This becomes very important because usually with contingency table, you want to ask questions about proportions, which we're going to talk about in a sec. So what do? You say, okay, how many people are in the STEM group? Well, I have 8 plus 7 plus 11 plus 39, right? So that is, I wrote it down, it is 65. So there are 65 total STEM majors in this data set, is what this is telling us. And similarly, we can do this for all of the rows. There are 65 total STEM majors. Well, if I add up the 4 numbers in social sciences, I discover there are 79 people in social sciences, 64 in humanities, and 59 in interdisciplinary. And you can do the same thing for the column. How many people had a none writing expertise? Specifically, 8 plus 11 plus 9 plus 15, which is 43. And I'll go ahead and fill in the rest of this table for us. So the reason this is useful, oh my goodness. The reason this is useful is because we can use this table now to answer questions about proportion of group membership. So as an example, what proportion of STEM majors are expert writers? Well, let's look. What proportion of STEM majors are expert writers? So how many STEM majors are there? There are 65. And of that 65, 39 of them are expert writers. So if I wanted to know what proportion of STEM majors are expert writers, that is specifically 39 over 65, which is 0.6 or 60%. Cool. As another example, what proportion of expert writers are STEM majors? Now notice the nuance between this. Instead of looking at row sums, we need to look at columns. Here are all of the expert writers. And it would appear, again, there are 39 of those expert writers that are STEM majors. But now we're thinking about 39 of the total number of expert writers, and the total number of expert writers is 81. So, in contrast to our previous example, there are 39 STEM majors in the group of 81 expert writers, which is 0.481 approximately, or 48.1%. So it's very important for you to think about the distinction, and I will kind of leave you with that and think about how to use contingency tables and what it's saying about the relationship between these two variables. So that, I believe, is actually all I wanted to do for this video lecture. Good luck on the first, I guess, actual quantitative homework, and I will see you all tomorrow.